Well, ladies and gentlemen, and again, welcome to you all, and thank you for coming here today. I wanted to tell you a bit about the aims and the objectives of the Barra Centre, the hallmarks of the Barra Centre. If we just stop to think about the challenges the world faces, there's many of them, but some of the key challenges are around clean water, around low carbon energy, and they're around efficient production processes where we use less water, less energy, and less goods to make the things that we enjoy in our standard of living. There's challenges around making complex healthcare products. Some of you will know that many of these challenges have large separations components. Some of you may be surprised because you may not know very much about separations, but in the process industry, something like 40 to 70% of the costs of producing products are entailed in separations, particularly separations related to molecules. So there's a huge opportunity to work on things that society needs and to work on solving the world's problems by working on separation technology. And for that reason, we decided that we would start this centre. And the aims of our centre are to create paradigm-changing membrane absorption science and technology, to disseminate our research broadly, including in leading journals. So we want to have an academic input and an academic reputation. But as well as that, we want to translate our research into beneficial impacts on industry and society. So we'd like the things that we research and the work that we do to have a meaning and a use for society. And then finally, we'd like to work collaboratively, partnering with industry and with other research groups. So they are the four aims of the centre. In terms of the type of research we want to do and the focus that we're going to have, our research focus is on developing innovative nanomaterials, including porous polymers, metal organic frameworks, two-dimensional films, and ceramics. So these are the engine, if you like, of what we want to do, of the developments we want to make and the breakthroughs we want to achieve. But in order to do that, we're going to need to turn those materials into useful things. We're going to fabricate these nanomaterials into membranes and absorbents for molecular separation processes. So we're interested particularly in separating molecules one from the other. In that work, we'll focus on spanning scales from molecular design of materials right through to pilot-scale manufacturing of membranes and absorbents. So we want to do fundamental scientific discovery and couple that with the production of things that can be used in actual processes. We want to work on the application of these membranes and absorbents to enable new molecular manufacturing platforms. So looking at fresh ways of producing products in the process industries. And then I think if you try to summarize that, the emphasis really is on understanding separation mechanisms and the engineering of separation materials at the molecular scale. So that is the overriding research ethos of the centre. And since that's a bit complicated in plain language, the way I look at it is we're control freaks, but we're molecular control freaks. So this centre is about molecular control freakery. We want to control materials at the molecular level, and we want to use those molecular materials to achieve molecular separations. The centre is named after Richard Barra. Richard Barra, FRS, is credited with breakthrough research in polymer membranes and in molecular transport and microporous media, particularly in zeolites. And it's interesting that the work Barra did was taken up by industry, and now zeolites are used ubiquitously. It's also interesting that he established this field of zeolite research and their applications in industry, but it's also interesting that there's a unit called the Barra, which is a unit of gas permeability, which is still used today, and this has been named after him. So when you read the Journal of Membrane Science and you find a paper about gas separations, you'll see permeability quoted in Barra, and that's named after Professor Barra. So as well as all his research contributions, he was also the head of the chemistry department here at Imperial College in London. And it's a great pleasure today to have one of Richard Barra's former PhD students, Richard Baker, who's here. He's already told me one or two stories that make me think the formality between supervisor and student and the level of deference and discipline was different back then than it is now. But Richard was a PhD student of Barra's. And we also, as Nick said, have Richard Barra's daughter and Christine and her husband here with us today. So that's a very nice symmetry to the whole thing, and I think makes a whole pleasant feeling to the starting of the centre. So the Barra Centre leadership team is myself, but it's not just me. I'm accompanied by Kang Lee, Brad Leidvig, Camille Petit. Camille had a baby only a month ago, so she's, I think, had to go off to take care of things there. Chile, in Chile Songs. There's 5 principal academics based in the Department of Chemical Engineering who are responsible for running the centre, but we're helped by a dozen affiliated faculty, and these faculty are based in chemical engineering, but also in the Department of Chemistry and the Department of Materials, and it's nice to see so many of them here today as well. So we have the core members who are focusing on fabricating materials and making those materials into membranes and absorbents, and then we have colleagues that work with us on, for example, the chemistry of those materials and on the simulation of those materials and on the imaging and characterization of them. So there's a total membership in the centre of nearly 20 academics across 3 main departments. As well as the academic members of the centre, we're very privileged to have an advisory board. So we've asked the leading people, or we think the leading people in the membranes and absorption community globally, to be our advisory board and to tell us if they think we're headed in the right direction. And if we're not headed in the right direction, they don't have to tell us what to do. I'm sure they're working on that themselves, but to give us some hints about how we can improve things. And we're very lucky to have Richard Baker as the chair of our board. And Richard's already told us his bit of advice, which is do something useful. I think that's pretty good advice. We have Professor Michael Weaver. We have Professor Marco Mazzotti. We have Professor Max Liu. We have Professor Susanna Nunes. And we have Professor Matthias Wessling. So we have a very distinguished group of people here with us today. They're sitting here in the front row. And my advice to all of the students and the postdocs here is if you can, make your way to them and pick their brains, talk to them, see what they have to say. I think they have a lot of useful input to give to the centre. So that's the centre staff. What are the hallmarks of the centre? The things that we want to be known for and we want to be associated with our centre. The first, of course, is world-leading research. And I already mentioned that we're molecular control freaks. So that means that the kind of materials that we work on and the materials... Camille, you are there at the back. So that is Camille is there, I just noticed there. So the materials that we want to work on will be materials that we can know their molecular nature and we can control the molecular structure of those materials. So we have zeolites, which of course Richard Barrow worked on. We have metal organic frameworks. We have linear PIMs, linear polymers, and we have network PIMs, so polymers that are networked with intrinsic microporosity. We have perovskite metal oxides, and we have 2D materials like graphene and things like boron nitride. So we have these materials which we can describe in a molecular way, and we want to fabricate those into things that we can use for carrying out separation processes. So the kind of things that we'll fabricate are membranes, and you can see there an example of a hollow fiber membrane. They're membranes containing MOFs, for example, with crystals. They're membranes where we have a support layer and a very thin film separating layer on top of them. And they might be things like membranes made from crystals, where the crystals come together and form a membrane, or even this mess here, which is a crumpled polyamide film, so very contorted donut-shaped layers of very thin polymer films. As well as doing that research, we of course need to disseminate it. Now, aim will be to disseminate that in leading journals. So some of our recent publications are here. We had a paper in Science on thin polyamide nanofilms, and here's a paper we had in Nature Materials on nanofilms with intrinsic microporosity. And this is some shots of cover articles that we've had in journals like Advanced Materials and Advanced Functional Materials. So we want to publish our research as well as in the archive of journals of the field, for example, the Journal of Membrane Science and Chemical Engineering journals. We want to publish a fraction of our research in multidisciplinary journals to reach out to a wider community and get them engaged with our research. Another hallmark of the centre will be that we want to do discovery research to make fundamental discoveries. We want to patent the technology platforms and protect them so that we can draw support for their industrialization. So we want to go from discovery research through patented technical platforms to industrial exploitation. And this just gives you one such story that we've done at Imperial College. So we came out with the invention of cross-linked polyamide membranes, which means that membranes don't dissolve when you put them in difficult solvents. This is non-cross-linked, this is cross-linked. We commercialized them as so-called Duramem membranes, and this is a picture of a GSK facility using these organic solvent nanofiltration membranes. And this will continue, we hope, to be a hallmark of the centre. Not only will we do this discovery research, we want to take that research, we want to scale it up, and we want to apply it in industry. So to do that, we need lab bench to pilot scale fabrication facilities. And for those of you that don't know anything about membranes, let me try and explain a bit what that means. Is when we do things at the lab scale, we take a solution of a polymer, for example. So we might take a few hundred mils of this honey-like solution here, and we spread it onto a spreader bar, so a casting knife, and we cast it onto a non-woven. So we move this bar forward, we put a fixed layer of polymer film onto this non-woven material, and we immerse that into water. And that essentially freezes a polymer film in a non-equilibrium state that gives us membrane separation properties. But as part of this idea that we want to do this discovery research and then scale it up, we want to be able to work at a larger scale. So this is actually in slow motion. He doesn't move this slowly. He's here today. So to scale it up, we'd have a much larger machine where we actually have a whole roll of material, perhaps 100 meters long or 200 meters long, and we drag this through a spreader bar, we spread the polymer on that, and then we cast it. So we can do these developments at the lab scale on very small amounts of polymers, and then we can take those and we can use much larger scale equipment to manufacture long lengths of membrane that we can use for producing scaled up type devices. And the sorts of device we might produce is what's called a spiral wound membrane module. So we would produce something looking like this. This contains a whole lot of flat sheet membrane. So the way you make this is by using what's called a rolling table. You have a permeate tube, and you have to lay down some adhesives and wrap the whole thing up. So as well as discovering new polymers, new MOFs, new materials that we put into membranes and making those on small sheets, we want to produce those in larger lengths, and then we want to assemble them into devices, at least at the small scale, which resemble the sorts of devices that are used industrially. And through that way, we'll be able to take our discovery research and apply that to industry for the benefit of society. In the membrane world, you've always got discussions between those that work with flat sheets, hollow fibres, and those that work with other shapes. One of the hallmarks of the centre is that we'll work with flat sheets, hollow fibres, we'll work with doughnuts and spirals. In fact, we'll work with all shapes and sizes. So we have the capabilities for doing flat sheet membranes, for making hollow fibre membranes, and we'll continue to work with all shapes and sizes of membranes. So here you can see a flat sheet membrane, that's an 8 nanometer thick film, and here you can see some inorganic hollow fibres that are prepared to give very thin tubes. So work with all shapes and sizes. We're also very interested in how you design and simulate membrane systems. So with our affiliated faculty, we work on how we go about simulating things at a molecular scale. So this, for example, is monomers, one in an organic phase and another monomer in an inorganic phase, and these combine to form a nanofilm at this interface here. And so we've got affiliated members who work with the molecular modeling of these films and how we go about understanding the nanoporosity of them. And that's at the molecular scale. At the plant scale, we still need to design things. So this is an example of the kind of simulator we would set up to do process design. This is work in an Aspen environment. And here we're trying to design a membrane plant by taking the parameters that describe the membrane's performance and putting them into a process where we're trying to concentrate a solute dissolved in a solvent. So we go all the way from modeling at the molecular scale what's going on with our membranes through to using simulation tools that can predict how those membranes will perform in processing applications. So that's another hallmark of the centre. We're also interested in the centre in working across all of the key media. So we'll make materials for water, for solvents, and for gases. And some of them will pose extreme environments. By extreme, I mean it could be highly acidic, highly basic, or very aggressive organic solvents. And in those materials, what we'll be seeking are materials that are stable, materials that are selective, and materials that have high permeance. And to give you an example of some of the challenges, this is a membrane that's been exposed in DMF, a very aggressive solvent, at 80 degrees C. That's not 800 degrees C, it's 80 degrees C. And triethylamine, and you can see the membrane is completely destroyed by that treatment after only an hour or two. So by working with other materials, new materials, this is a polyether ketone membrane, you can see that that remains very stable. So this is an example of chemical stability. We work with making things stable in chemicals. On the right-hand side, you have an example of stability over time. As you improve or increase the permeance of membranes, many membranes suffer from aging, so their permeance goes down over time, And this shows you a membrane that we've recently made. We've made a membrane which has a high permeance but maintains that permeance over time by putting it on a robust support. So we'll be interested in materials for all media, for extreme environments, and we'll be interested in their stability, selectivity, and their permeance. We'll also be interested in multifunctional materials, so materials that can respond to their environment by changing their structure to carry out certain separations, and we'll be interested in combining materials with catalytic systems. So here you see an example of the water-gas shift reaction, where we're using a ceramic material to carry a catalyst. So we're reacting carbon monoxide and water to give CO2 and hydrogen, and if we can make a hydrogen-selective membrane, we can remove the hydrogen from that reaction and so shift the equilibrium to shift the equilibrium in that water-gas shift reaction and get more of the desired product. So we'll work with membranes that are also functional, catalytic, and other functions. And then the other thing that we will do is, as well as making membranes, we'll also work on the applications of those membranes. So membranes have to be used in some kind of process or to achieve something. And we'll work on platforms where we're using membranes to enable things that we couldn't previously do easily. This example here shows you a pharmaceutical production process where there's a first reaction which has been carried out in a DMF solvent, and that's run in a continuous reactor. And that first reaction then has to be passed to a second reaction where it's being a reduction reaction based on an iron catalyst in a packed bed reactor, but this reaction is happening in ethanol. So by using a membrane, what we call a membrane cascade, it's a series of membrane steps here, we can take the product of the first reaction, and without needing to evaporate the solvents, we can change that over to ethanol and carry out the second reaction. So that's an example of a membrane-enabled production platform. And we will use our membranes and absorbents to enable new production platforms. Another hallmark will be the partnerships we have with industry and academia. So we're very interested in partnering with people. We don't have all of the expertise we need in-house, and we know there's lots of other smart people out there, so we'll be interested in working with them, and we'll collaborate in multidisciplinary projects. And this shows you a couple of examples here. One project we're already involved in is the BP International Centre for Advanced Materials, and this is working with industry to develop novel materials for oil and gas applications. And another one is the GSK-supported Engineering Medicines Lab, where we're looking at the convergence between engineering and medicine to go about producing complex healthcare molecules. So these collaborations that we engage in will be a hallmark of the centre. And the last hallmark I want to touch on is to do with our researchers. So we have excellent researchers from diverse backgrounds. There's chemical engineers, physicists, chemists, material scientists. They all love coming into the lab each day to work on separation challenges. And one of the hallmarks of the centre will be the excellence of the researchers that come out and pass through the centre. So with that, I hope that you'll connect with us on any of the social media that we're connected to. Again, I welcome you here to the opening of this centre, and I hope this is the beginning of a long association that you have with the Barrow Centre. And I'd like to hand over to my colleague Kang Lee to tell you a bit about the research we're doing in ceramic membranes. Thank you.